So something you've never heard before. When a triangle contains a line that is parallel to one of its sides, the two triangles formed can be proved similar using the angle-angle similarity postulate, like this. Two parallel lines cut by transversal, we know that those two angles are congruent. This transversal, we know those two angles are congruent. Angle A is in both triangles, it's congruent to itself. Pick any two out of the three pairs you want, and you can use angle-angle similarity postulate to prove them similar. Once you know they're similar, you know their sides are proportional. We've seen figures like that. We've solved a few problems like that. Using similar triangles is good stuff. It works. There's nothing wrong with it. The triangle proportionality theorem makes a figure like that one even easier to use. Okay? The triangle proportionality theorem says that if a line is parallel to one side of a triangle and intersects the other two sides, I would have said something like, if you have a triangle with a segment inside it that's parallel to one of the sides, okay? Their wording's probably better for whatever mathy reason. Their wording is probably better. But anyway, it looks like this. You have a triangle, and inside of that triangle, you have another segment that connects with two of the sides and is parallel to that third side. The triangle proportionality theorem goes on to say, then that segment, the BE, the extra segment, divides the sides that it intersects into segments of proportional lengths. Oh, that's kind of hard to understand. What it means is this, that whatever that length is to that length, make a ratio. And it equals the ratio made from that length to that length. For instance, maybe this was like 3, 2, 6, and 4. So the triangle proportionality theorem says the ratio you make from 3 to 2 is equal to the ratio you make with 6 and 4. Okay? So can you use a figure like that, or when you see a figure like that, can you simply use similar triangles to work everything out? Yes. But look how easy that is. So for instance, if that was missing and it was an x, that'd be a really easy proportion to solve, wouldn't it? So the triangle proportionality theorem is really useful. It doesn't apply to a lot of different things, but when it applies, it's really easy to use. And I think you need to know it. So let's do a couple. From page, let's see, page 489. Let's do number 1. All right, and I've got a head start on you. I've already got these things labeled. You don't have to draw the figure, but just watch what I've got and write down the proportion I write down. So if xm equals 4, so I've got that length labeled. Xn equals 6, I labeled that. Nz equals 9, I labeled that. Find the length of xy. Now, instead of finding the length of xy, I'm going to find that length. Once I get it, what am I going to do to get the length of xy? Add 4 to it. Okay? So according to the triangle proportionality theorem, make a ratio 4 to x, make the ratio 6 to 9, and those two ratios must be equal. Right, it doesn't matter. I could have done x to 4 equals 9 to 6. It will get the exact same thing. Okay? As long as you're doing the corresponding parts, the corresponding segments, then you're fine. Okay? All right, so I can reduce that or not. Cross products would give me 6x equals 36. I get x equals 6. Now, I'm not finished. That's what x equals. So what's the length of xy equal? 10. And you can see I would have gotten the same thing as the other one because my next line is the same, so I know I'm going to get the same answer. Number one makes sense? All right. Number two. Now, sometimes with the triangle proportionality theorem, you do have to do a little arithmetic. It's always either adding or subtracting. Okay? So the length of xn is 6. I labeled that. The length of xm is 2. I labeled that. The length of xy is 10. I labeled that. All right, now, look. If xm is 2 and xy is 10, do a little subtraction. What's my? And now I can use the triangle proportionality theorem, can't I? Supposed to find the length of NZ, so I called that X. So make a ratio out of 2 and 8, make a ratio out of 6 and X, set them equal. So 2 to 8 equals 6 to X. You can reduce the 2 to 8 to 1 to 4 or not. Either way, you get X equals 24, don't you? And now, number one, I had to take my answer of X and do something with it to answer their question. For number two, do I need to do anything with that 24? No, that's it. The length of NZ equals 24. All right, one more straightforward example of the triangle proportionality theorem. Number 7. All right, I outlined the triangle with blue and then the extra segment with blue, and I tried to mark them parallel. I think you can see it okay. It says refer to the map at the right. 3rd Avenue and 5th Avenue are parallel. So those two vertical segments on the drawing are parallel to each other. If the distance from 3rd Avenue to City Mall along State Street, so State Street is the horizontal segment at the bottom, is 3,201 feet. So look what I did. All right, there's 3rd Avenue, there's City Mall. So that whole distance is 3,201 feet. Notice they've already labeled this distance for us. Okay? Find the distance between 5th Avenue and City Mall. Well, look, 5th Avenue, City Mall, along Union Street. So that distance right there is what they want us to find. Notice they've already labeled that one for us. So if you get rid of all their fancy talk, what we have is 1056, 1162, and I do need to figure out that other missing segment, don't I? So just subtract. 2145. And now I can use the triangle proportionality theorem. So far, so good? All right, now we're going to get big numbers. Well, so what? We have calculators. So 1,056 to 2,145 equals 1,162 to X. Are we good with that proportion? All right. Reduce that one on the left or not. Do cross products. I'll get 1,056x equals, how big is this? That's 2,492,490. Divide both sides by 1,056. And what do you get? 12. I got 2,360.3125. And they said to round it. Nah. I like exact answers, even if they are ridiculously precise. So, 2,360.3125. Oh, feet. It looks like two F's. Let's see if I can turn that into a T. Here we go. Feet. All right. So, is the triangle proportionality theorem your friend? Yeah, I think so. All right, that's pretty good stuff. It only applies to that one certain type of figure, but when it applies, it's easy to apply. All right. Well, the converse of it's also true. So, when we know that segment's parallel, we know that the two sides are divided up into congruent or into equal ratios. If the two sides are divided up into equal ratios, that's enough to prove those two segments are parallel. So the book shouldn't have marked those as parallel yet. If we know that that ratio, AE to EB, equals that ratio, CD to DB, then that's enough to prove the two segments are parallel. Okay? So out of all those ways we already knew how to prove things are parallel, there's another one. Number 3. In triangle ABC, the length of BC is 15, BE equals 6. So if BC is 15 and BE equals 6, what's the length of EC? 9. DC equals 12, AD equals 8. Determine whether or not these two segments that I'm coloring in red are parallel. Well, if the ratios are equal, then the converse of the triangle proportionality theorem says, yes, they're parallel. If the ratios are not equal, guess what that means? Then they're not parallel. So let's see if they are. 6 to 9, does that equal 8 to 12? Yeah, in fact, can't you do that one in your head, reduce them? 2 to 3? If not, do cross products. Using cross products is just as valid a way to see if two ratios are equal as reducing is. So we say yes, they're parallel. Any questions on number 3? We good? All right. Give number 4 a shot and see what you come up with. You got to do a little subtraction before you write your ratios. Yes or no? No. 5 to 10 doesn't equal 4 to 9. If you tried cross products, you'd get 40 and 45. And if you try reducing, you get 1 to 2 and 4 to 9. So, no. All right. We still good? All right. Triangle midsegment theorem. Oh, you might not have known triangles had midsegments. We knew that with trapezoids, right? In a trapezoid, the midsegment connected the midpoints of the legs. In a triangle, there's not one midsegment like a trapezoid has. There's actually 3. Connect the midpoints of two sides, and you've got a midsegment. So the formal definition, a midsegment of a triangle is a segment with endpoints that are midpoints of two sides of the triangle. So look, every triangle is going to have 3 midsegments. It has to. So if R, P, and Q are the midpoints of those 3 sides, then the segment from R to P has to be a midsegment because it fits the definition. Segment PQ has to be a midsegment. It fits the definition. RQ, midsegment. Definition. Okay? Now, the triangle midsegment theorem says that a midsegment of a triangle is parallel to one side of the triangle. And it's kind of easy to tell. It's parallel to the side it doesn't intersect. Okay? And its length is 1/2 the length of that side. So a midsegment is parallel to one side and half as long as that side. Midsegments parallel to a side, half as long as that side. Well, that's easy. I mean, really, that's easy. Look at number 5. They tell us that segment JH is a midsegment of this triangle, and they want us to find X, which is the length of JH. So JH is parallel to KM by the triangle midsegment theorem, and it's half as long as KM. Bet you don't know what half of 22 is. Yeah, it's 11. Look, I did bonus work. I showed my work. Isn't that good? And I know what you're thinking. That's too easy. There's got to be a catch. Here's the catch. Number 6. JH is a midsegment again. So it's half as long as LM, but they don't tell us LM. So if JH is 5 and it's half of LM must be, yeah, that's as hard as it gets. And I showed my work again. All right, so you ought to be loving triangle midsegments. Okay. We're getting close to done. All right. Remember how a corollary is a theorem that follows from a theorem? Well, that's what a corollary is. It's a theorem that's a direct result of another theorem. This corollary is a direct result of the triangle proportionality theorem. And look, you got to realize when I say a direct result of, to a mathematician with a PhD, it's a direct, obvious result of. To all the rest of the normal people in the world, we just go, okay. All right, so the proportional parts of parallel lines corollary says, if 3 or more parallel lines intersect 2 transversals, so look what has to happen in your figure. You have to have at least 3 parallel lines, 1, 2, 3, and at least 2 transversals, 1, 2. If 3 or more parallel lines intersect 2 transversals, then they cut off the transversals proportionally. In other words, the distance from there to there, make a ratio, then with the distance from there to there, and then do the same thing over here, from there and then to here, and those ratios are equal. Let me put some numbers on there and show you what I'm talking about. So for instance, if this was 2 and 3, then over here that would be 4 and 6. 2 to 3 equals 4 to 6. And then you solve problems about like the triangle proportionality theorem gave us, okay, where you'll know 3 of those, figure out the 4th one. All right? Let's do, let's hold off on it. Let's do this next. All right? This corollary comes from the corollary we just learned. If 3 or more parallel lines, all right, 3 or more parallel lines, cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. Now, congruent segments. What's the ratio you make out of congruent segments? What would, if the segments are both 4, what's 4 to 4 reduced to? 1 to 1. What if they were both 7? What's 7 to 7 reduced to? 1 to 1. So congruent segments always give you a ratio of 1 to 1. So look, we just learned that the ratios are congruent. So if the ratio happens to be 1 to 1 on one of the transversals, it's got to be 1 to 1 on every transversal. And ratio of 1 to 1 means they're congruent. Okay? So since AB is congruent to BC, we conclude that EF is congruent to FG. All right? So like if we know that's 4 and that's 4, and then we know that one's 3, then what's the length of EF have to be? 3. Okay? All right. Oops. Number 9. We're going to do number 8 as well, but number 9 first. All right, on number 9, we have 3 parallel lines, and we notice that on one of those transversals, the 2 segments are congruent to each other. That means on every transversal, the segments are congruent to each other. So we know for a fact that 1/4 x plus 6 has to equal 2x minus 29. Well, look what you've got now. We don't even have ratios anymore, do we? We've got congruent segments. So to solve for y, just set 12 minus 3y equal to 16 minus 5y. And solve it. So I added 5 to both sides to get 12 plus 2y equals 16. Subtract 12 from both sides to get 2y equals 4. Divide by 2, y equals 2. It's been a while since we just set 2 things equal to each other, hasn't it? Just set them equal to each other. Same thing over here to get the x. 1/4 x plus 6 equals 2x minus 29. Now, on this one, since we do have a fraction in it, let's clear fractions. Let's multiply the left side by 4 and the right side by 4. On the left side, 4, distribute it. 4 times 1/4 x is x. 4 times 6 is 24. On the right side, distribute the 4. 4 times 2x is 8x. 4 times negative 29 is negative 1/16. Then I subtracted x from both sides. Then I added 1/16 to both sides. Then I divided both sides by 7. All right, now, back to number 8. We okay with 9? All right, the reason I skipped 8 is I think they must have messed up here. There's no mystery. They've got 2 segments marked congruent that have y's in them and 2 others marked congruent that have x's in them. I think they just told us more than they meant to. I think they meant to tell us maybe that these 2 were congruent and then have us realize, oh, even though we don't have the 3 parallel lines, we would think since those 2 are congruent, that's a ratio of 1 to 1. When I make a ratio out of the other 2 segments, they'll have to also be congruent to get a ratio of 1 to 1. They told us too much. So 3y equals 1/2 y plus 20. 20 minus 3x equals 2x minus 5. Solve those 2 equations real quick, and then we'll compare answers. Did you get the same answers I got? Okay. Any questions?